Today we're pleased to have Marcy Robertson talking about topological inspiration for infinity modular operads. So whenever you're ready, thanks, Marcy.
All right, great. Well, hi everyone, and greetings from Melbourne. So thanks for coming a bit later than your normal time for me on the other side of the world. So I'm going to talk to you today about a really long ongoing project I've had, which was to think about this interesting group called the Graphical group, and how it had led to the idea of an infinity modular operad. So along the way, I'm going to mention joint work with like some subsets of co-authors. So the categorical stuff is all done with Phil Hackney and Donald Yao, and the geometric parts are with Luci Bonatto, Pedro Boavida, and Geoffroy Horel. So it's a mixed up bag. All right, so I'm going to start with just the motivation. Like, what are we trying to do? So a really fast intro to a lot of cool math, by which I mean this is the first part of SGA1 from Grothendieck. And let's let Gal Q be the absolute Galois group of Q. So this is a big profinite group. This plays a really important role in algebraic number theory. And a profinite group is by definition, I'll get my little guy here. So profinite group, when it's profinite, I'll write this little hat on top, is an inverse limit over all quotients of the group by subgroups with finite index. So it's just, we need to know a bunch of finite quotients of the group. So if I want to write down an element in G hat, I'm going to need to know its projection onto all of its finite quotients. But in fact, while we know that the absolute Galois group Q is profinite, we don't actually know the finite quotients of the absolute Galois group. So in fact, we don't really know what elements of this group look like. We can write down the identity and complex conjugation, and that's about it. Maybe someone can write down one more element, but I don't know them. And so the idea of Grothendieck was to use the fact that the absolute Galois group shows up in geometry, specifically in when you're looking at moduli spaces, and try to determine if we could use the actions of the absolute Galois group to tell us what the elements look like. So can we identify groups, little elements G, with pairs of elements, one being an integer, a cyclotomic character, and one being this little f sub G, which is an element in the free group on 2 letters. So this is just a free group. So just words in X and Y. And this came from the fact that, and this will be the big role that we're playing today, that while the free group on 2 letters can be identified with a mapping class group, which I'll tell you what that is today. It's really the fundamental groupoids of the moduli space. So if these words don't mean much, that's okay. I'm just trying to say, so what I'm really aiming at is, can I find necessary and sufficient conditions for an element of a group that I don't understand to be written as a nice pair where I do understand them? And in order to do that, then I'm going to break down this element, right? So I'm going to do this thing that we do in math, which is, here's a hard thing I don't understand. I'm going to make it a little bit easier. And then I'm going to keep simplifying.
A clarification, Marcy. So is the F2 prime that you wrote an arrow to the same as the F2 on the next line? Was that a typo, or is that the same group or not?
No, it's actually the derived subgroup of F2. And I forgot to delete the prime because it's not, there's a part of me that can't be that imprecise. So I want FG to be in F2 prime. So this would be a particular subgroup of F2 where automorphisms are of a certain form. It'll show up later, but you can. This is supposed to be F2.
Okay,
so,
thanks.
Yeah, no worries. So that's like too precise for this level of discussion, but apparently a habit. Anyway, so I want to tell you about a slightly easier group. So right? There's this intermediate guy, GT, and then subgroups of it, and that's where the motivation for this big categorical machine, which will be the majority of what we talk about today, comes from. So I just want to tell you some notation. So like, because I want to just give a definition. So there's this group GT that I can write down. So this was due to Drenfeld in a paper in the 90s, I think 94. Introduced a new group that was kind of like the absolute Galois group, but we can actually write it down. And so before I give you the definition on the next slide, just some notation. So the free group is just words in X and Y, potentially infinite words, but just words. And then if I map to any group G, right, that's necessarily going to take X and Y. I forget to use this thingy. It's going to take X to some generator A and Y to some generator B. And I'm just going to write this notation F of A, B for the image of a word, right? So if my map is the identity, then right, F is F of X, Y, like that, right? X goes to X, Y goes to Y. And if it's the map that flips X and Y, I write F goes to FYX, just so I can keep track of the fact that I'm looking at the image of F2 in various groups. Okay, and you don't need to know this definition. I just want to show you that it has one. So the Grothendieck-Teichmüller group, this group that Drenfeld defined, GT, it's this big profinite group. And look at what it is. It's elements lambda f, which are integers, and elements f in this free group on F2. So this is the prime, David, satisfying the property that if I map x to the lambda and y to f inverse y lambda f, that's an automorphism F2. So this is the prime. That's that thing. And then I just have three relations, right? And where I introduced that notation before, so you know what I mean here, I mean that I have f of xy, f of yx equals 1. So think about this as maps, right? This is, yeah. I have f2 hat, the identity, f2 hat. And then this is this x goes to y map, f2 hat. And then I want this whole thing to be the identity. That's just where I introduced that notation. And the third relation is taking place again in this mysterious gamma. Oops, there's a hat there. This gamma, which is a mapping class group. So I just want you to know this is a presentation. Yep.
Can I interrupt for a moment? In item 1, should that, the left side of the equation, f of xy, f of yx, what you've written after that is a composition of maps, one of which is an identity, but I think you probably meant the product of the two values rather than the composite of the maps.
That's right. Thank you. I do mean the product of the two values. I'll just erase that on that. Yes. Yeah, that's sloppy. Just to point out like where these, yeah, the image under this map. Thank you. Right, so the point of me putting this big ugly definition up is to say I have a definition. So I told you I didn't understand what the absolute Galois group looks like, but I do have a definition here. I have a presentation of my elements. And in fact, there's it's a very nice theorem of Ihara. It was mentioned by Drenfeld and proved by Ihara that there's an injection of the absolute Galois group Q into GT. And so we're going to refine GT by studying these mapping class groups. Okay? So we're going to put GT as our stand-in for the Galois group at the moment, and we're going to refine it easier. Oops, did a little weird wiggle. Okay, there it is. Okay, so now we can refine our question further. So I want to understand what an element of the absolute Galois group is. And I'm going to say, well, what now is the Grothendieck-Teichmüller group? What does this group look like? So I have a few observations, right? F2 hat is this mapping class group. Just in case there are experts in the room, I'm identifying the orbifold fundamental group with the mapping class group here. And if you don't know what that means, then don't worry about it. there is an isomorphism there. It's just hiding something kind of fancy. And the relations in GT, well, these are coming from mapping class groups, right? That third relation I had at the bottom, which is a pentagon relation. It's actually the same pentagon from braided noidal categories. That's also living in the mapping class group. And I know a lot about mapping class groups. So a beautiful theorem by Hatcher and Thurston in the 80s tells me that it's in the 80s, that in fact, I can write down what every mapping class group looks like. So what is a mapping class group? So it's going to be diffeomorphisms of surfaces. So here's a surface. And I'm going to give it this group a presentation, and it's going to be generated by certain diffeomorphisms. So here will be some alpha around a curve. And in fact, they're very well prescribed curves around each of these little holes here. And I can choose every presentation based on a choice of curves on a surface. Right? So I know what a mapping class group looks like always. It's well prescribed. If just question, like if people aren't familiar with this surface that I wrote down, this is like a donut. I can't draw it very well. It's a genus 1 surface, and I just kind of like stabbed it 4 times. So, and then like made the puncture wounds look a little bit nicer. Okay. So in other words, so I went from something I can't write down to something big, but I can write it down, to now a really nice group where I understand, and it looks like it's made up of spaces and very easily understood relations here. These relations I won't tell you about because they don't play a role in today's talk, but we can use this idea. And in fact, what am I going to get from this idea? So my mapping class group, those curves, so the alphas, the generators of my group, they come from canonical pants decompositions of a surface. So if I let my surface, this is a surface here of genus 1 with 2 points. So G for genus, N for the number of times I've stabbed it, 2 boundaries. If I take a pants decomposition, so this is going to be a collection of curves on a surface that cuts this into pairs of pants. Okay, so a pair of pants is a surface that looks, oops, it's kind of an upside down pair of pants, like that. So this is pants. I don't know where the origin of that comes from, but every topologist I know calls them pairs of pants. Looks kind of like a boomerang. But, I've been in Australia for a long time, so maybe that's me. All right. So a pair of pants decomposition. So what am I going to do? I'm going to choose 2 curves here. If I choose my alpha 1 and my alpha 2, and you can imagine slicing up this surface, well, what would the result be? I would have this pair of pants with my red from this piece. I'll make this blue. And then I'd have another pair of pants from the purple. Right? So I cut this guy up. So every time I cut a surface into a pair of pants, I get my generators for my mapping class group. But this is kind of interesting because pants decompositions actually look like compositions. So if you want to change your perspective on what the object is, so if I start here So on this side, I have a pants decomposition. And I'm thinking about, okay, that red circle decomposes this surface into, so this is the pants decomposition of a surface of genus 0 with 4 boundaries. And that red circle is the thing I cut along. Well, it also can be a thing that I've pasted along. Right? I can also think about there was some composition where I glued these 2 red circles together. And now I have obtained my pants decomposition. And if I want to see an example of a higher genus case, right, I can pick a pants decomposition here. So here's my alpha. Well, this looks like a kind of trace operation or composition where I've allowed the gluing of these 2 pieces. And so I can like just kind of glue up the pants there. So a pants decomposition of a surface could instead be thought of as a composition of an object. Okay? That's the perspective that I want to take. So what kind of object has compositions that look like this fundamental thing? And that's where we're going to sort of shift the tone of this talk for a bit into something kind of categorical. They're modular operas. So it's a type of categorical object that allows me to think about surfaces, all possible surfaces, all possible compositions at the same time. Okay? So I can sort of study the whole by creating the right object that models these pants decompositions. All right, so oops. So I want to start with a pretty abstract definition. So a cyclic operad, so this is, for traditional reasons, you always define modular by going cyclic first. So a colored cyclic operad, so this is kind of like a category where we have an involutive set of colors or objects. You can think of these as objects. And involutive, I mean, so I have a set of objects and I have, you know, I with I squared equal the identity. And for every sequence of objects, I'm going to have a set of operations or morphisms that I think of as being a little spider. Like this. And I'll put a little f there to be idea. So the idea is if in a category you have from x to y and you have a morphism f, here, my objects are these edges and whatever's at that vertex is the operation here. So it is I have a set of operations, so like n-ary operations. And I'm just going to allow, sigma n means that I'm going to allow a permutation of the inputs around the edges there, right? So I don't really care the order of the things going in, but whatever f is somehow composing or modeling those objects. Okay. And then I'm going to have together with that some nice compositions where I'm allowed to glue one spider to the next. Let me move this guy. If I have some kind of decent color matching, so here's a G. I'll call this D. And I can map these together. And this would be some kind of composition in this object. And I do want somehow like the colors to match, but just like in a category, right? You don't just compose any morphism. They have to have some domain and codomain identification. So thinking about that in the picture that I drew, right? I had some object here. I have some object here. And I'm identifying here, I guess this was my D1, and this is some C2. And the gluing, this pants decomposition is corresponding to the composition of C2 with D1. Like that. Yeah.
So Marcy, are you saying that you're composing these two arrows and that you need C2 to equal D1 as objects to do it?
Yeah, I need them to exactly. These are arrows. These pants are arrows for operations of some kind. And yeah, I need this. I need D1 to match C2.
And is the involution involved? Maybe you're about to say all this and I'm just jumping the gun here.
Oh, yeah, the involution, you can think of that as like orientation in this context. So I do want, here, I want CI to equal DJ dual so that like I can match the duals around. In this case, think about it as in like a direction. So here, if I'm going up and this is going down, I want to match the orientation so that everything glues together. So
thanks.
Yeah. Now, a modular operad, I should say an example maybe for this audience that might be more familiar is that, for example, star autonomous, I'm going to spell this wrong because I didn't plan it. Star autonomous categories are examples of cyclic operads. If you want an explicit reference where that's worked out, catch me at the end of the talk and I'll find it. I know the paper, but not the example. So they're like categories with no direction on the morphisms. And I don't really know if I'm going in or out, but I can choose. And I have a sense of composition. Now, a modular operad is like when I have this extra operation of self-gluing. It's like a trace or a formal, I mean, it is a formal notion of trace. So it has a contraction operation, which means that I can go from here, a bunch of some little star living in P C1 through Cn. And if I have a reasonable matching of duality, I can contract down to a loop. Like that. It effectively takes, so if you're thinking about vector spaces, it's like if I have two, if I'm looking at multilinear maps and I have a V and a V dual, I contract down to K. I contract down to my original field. That's actually an example. Yeah.
I think something earlier in the name cyclic operad. What is cyclic here?
The cyclic is from the idea that you can permute all the way around, like that. So there's no distinction of input and output. So traditionally, there's this object called an operad, which has like inputs and a distinguished output, like this. And then cyclic is that we no longer want to distinguish inputs and outputs, and so you can go around like that. I think that's
Thank you.
That's it. As yeah, no problem. All right, and going back to our picture, right? What was our example of a modular guy? Well, right, I had these two objects. I had this, I can think about my tree. And the contraction, oops, it's supposed to be red. maps these down to this pants decomposition. So my pants decompositions are encoded in modular operad compositions. All right. So this is almost the right thing for studying the modular operad. The definition's fine for studying all of these mapping class groups. What happens though is there's this hat hanging around, and profinite completion doesn't behave very well with respect to products. It's usually okay on groupoids, but when we want to look at topological spaces, it's very, very, very rarely product preserving. So I want to weaken what I just told you and create like an infinity model. I want to take this model all the way. Okay. So I want to tell you about how to rewrite modular operas, what I just told you, as pre-sheaves of graphs, right? Graphical pre-sheaves, and how they can be rewritten in graphs. Okay. So by graph, this is a picture of a graph. I'm going to mean something where I have vertices, which are my teal dots, and then edges between them. And I'm going to allow my edges to not always touch a vertex. So I'm going to allow, for example, a free floating edge, so no vertices. And I'll allow legs like this to not touch. So it's not a closed graph, as some people might use. And the only thing I won't allow is this free floating loop. And that can be handled. I just don't want to bring, it adds a complication I don't want to talk about. So, but that's the kind of thing what I mean by graph. Okay, so specifically, I'm going to give you a combinatorial definition of a graph. This is what's called a Feynman graph by André Joyal and Joachim Koch in a paper they have. And a graph is just a diagram of finite sets. So we have a set of vertices. We're going to have a set of half edges, which is, I just sort of weirdly misspelled, set of half edges where and an involution, a free involution on them, so I can glue edges, half edges together. And then a partial defined, this is just D is for domain. So not all edges will necessarily be attached to vertices. So this is just domain. All right, so these are the, i.e. equal the half edges attached to a vertex. All right, we're definitely going to get a cat in this one. She's right there. Okay, so here's my example. Right, I have two vertices, and I'll have a set of half edges. So this will be, for example, A1 and then A1 dual is living there. A2 dual, A3 dual, A4 dual, and A5. I hope you can read that. Got a little squiggly there. If you can't read it, please let me know. So here, right, A is this, you can think of each of these as like a half interval, right? So this is going to be A1 dual, dot, 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 A5 dual, right? D, these are the things that are attached to my vertices. So A2, A1, A3, A4, A3 dual, A5, A4 dual, and that's it, right? And the involution then tells me how things are glued together, right? So you don't have, it just tells me which edges are formed. So an edge is like an orbit of the involution. Okay. And I want to form a category out of these things. And so I'm going to define graphical maps to involve blowing up vertices in a very particular way. So,
Wait, Marcy, can I ask another question?
Yeah, of course.
Did you demand that the map from D to E be injective?
D to, no, just A.
Yeah, A, sorry.
Yeah, this is just so that it's a subset.
Oh, I didn't read it. It was right there. Okay, thank you.
Yeah, sorry. But that's actually like a super good question. Yeah, but not to B. That's not fair. But yeah. Yeah. So we're going to blow up the vertices. So we're going to allow things like, I'll use a highlighter. So if I play around with this vertex, well, I can map it over here to this vertex. And the only thing, so I'm going to require that, for example, the arity around the inputs should be preserved. But I'll allow things like that you can collapse and contract the edges here. See that these two edges got identified into a loop. And I'll also allow, on a different, maybe this guy's pink. Well, in fact, I can graph substitute. I can blow up this vertex with any other graph. So in this case, this entire graph got substituted into this pink vertex. And why is that allowed? It's allowed because I'm preserving the number of legs is still 4. So as long as I have some local data that's an isomorphism, which is the number of edges that are like free, I can shove any other graph inside. So see, because these are loops, they don't add any boundary to that graph. And that will be a nice graphical map. Now that's a picture, and the actual definition is annoyingly complicated, but you can break it down into 3 basic graphs. So there are 3 basic types of map. So one is called an inner coface map. So I can take any graph. So this is my G. And if I can blow up a single vertex V, in this case, I'm focused on this vertex here, by a single internal edge, I'll call that like by adding one internal edge, I'll call that an inner coface map, right? So in this case, what have I done? What this picture is depicting for you with the little picture on top is this is the graph that I have shoved into this vertex. And now the result is here. Okay. And again, in this other direction, well, I can add something as long as I have one loop. I only want to add an internal edge. So this loop. So here I've shoved this graph into that vertex. So those are the 2 types that I can get for this really basic thing. And you can iterate, obviously, to get something more complicated, but these are the elementary morphisms.
Is it that, sorry, just a little question. So you can't like go backwards. So you can always add vertices, like you can replace one vertex with like an entire graph, but you can't take like a chunk of a graph and replace it, like do the opposite operation. This isn't allowed.
No, we're going to not allow that. The only thing we're going to allow is to cancel like single vertices that have just like one edge on each side, which is my 3rd class map. But we're not going to allow you to just like get rid of a big chunk.
So there's no way to like, you can only like increase like the homotopy or whatever. Like you can only like make things more complicated somehow. Like you can't cancel stuff.
That's
down.
right. We're going to keep like an elementary. Yeah, so we'll have some like generating elements this way, and you won't like the corolla. So this way, basically you can say every graph starts from something like that. And you can say that in a really systematic way. which is where we're going for the modular operads. Yeah.
And not to tell me if this is jumping ahead, but are these things called coface maps because there's some kind of like simplicial or dendroidal structure, or is that just a
Yes.
name for a different reason? Or like, okay.
No. It's implicit. It's to be generalizing the dendroidal set for modular operads. Is the idea. Yep. And yeah, so an outer coface map, oops, I randomly highlighted, is going to be a type of embedding or inclusion. So here by embedding, I mean, you can think of it as just a locally injective. So I want to have a map where I just add one internal edge. So either I glue two little legs like this, or I just look at an edge mapping, right? I'm going to give a special thing where I can map an edge to things like that. And those are my only options. So here I've glued. So it's locally around the neighborhood of every vertex. It's an injection. That's what I mean by embedding. And then as you ask, can you ever get rid of something? The only thing we're going to allow you to delete are codegeneracy maps are vertices of the type with like one input and one output, and we'll allow those to be deleted to an edge. And that's the only thing we're going to allow, that where you basically think of it, you're blowing up the vertex by sticking an edge in there. Right? It's still technically a graph substitution where we just have this one graph that kills vertices, which is the edge. Right? This free floating edge was allowed as in my formalism. Okay. And so that's a category. So I'm going to define a category. It's U. The reason for the letter U is because we couldn't find another letter that looked like undirected graphs that was not already in use. So it's U. Someone can tell me what a name is a category. So our objects are connected graphs. So these just weird combinatorial spiders. And the morphisms are all given by composites of inner coface maps, outer coface maps, codegeneracies, and isomorphisms. So this generates everything. All right, and as mentioned by Tim, right, we're going to be able to look at this now as a replacement for a simplicial category. So if you want to think about categories as being simplicial sets, you can I'm about to sneeze and I keep making like a weird face. So now this is on video for all of you to know. Anyway, so category graphical sets. So this is pre-sheaves over U. So what do I mean by that? I mean functors from this category you opt to set. Okay. So an element of this category is a functor, which means, what does it mean? So I'm going to write xg for evaluation of x of g. What do I mean by that? Here's my graph G, right? And I want to take this now to what I think of as like the set of decorations of G. Right. So I'm thinking of, remember I was thinking about these as elements. I was thinking about G or as like elements of my modular and cyclic operad. I'll try to draw the same guy here. And so what I'm really thinking about is, well, this could be a morphism F, and this could be a morphism G. And this is, but there might be other composites in the shape of G. So I want like the set of all decorations of this graph, right? That's what X sub G means. And then because it's the opposite category, every graphical map gets flipped around. That's what this second point is saying. Right. And so to get to why this looks like a modular operad, I want to build for you a special graphical set made of internal edges, which I'm just going to call X sub 1. Some people might call it like a Corolla ribbon or necklace, something like that. So I'm just going to show you by picture what it is. So I want this to be made of internal edges. So I have E1, E2, and E3. So let's let X be a functor. And here's V1 and V2. And I can build a diagram now of X by looking at how my vertices and edges map up. So I'm going to write E1, E2, E3, and V1, give it a little space, V2. And I'm just going to now write down, just draw for you how E1 is attached to V1, right? And E1 is attached to V2, and so forth. So this is a diagram, right, of how the edges are attached to the vertices. So now if I think about this in terms of my pre-sheaf category, well, I'm going to go back and I'm going to write, all right, this is X of an edge. All right, this is X of, and I'll even label it. And X of an edge, E3. And here I'll think about the decorations of V. So this should be like the star, the little graph at V1. So by star, I mean like this little graph that's sitting in there. And then because I'm in the opposite category, I'm going to change my arrow directions. Hopefully I won't delete the whole lines. Like this. And now I can take the limit. And if I take the limit of this diagram, this is some special guy I call X1 equals the limit of this guy. What I wrote here as star V W. So why am I telling you this crazy thing? This is capturing composition. So this weird thing that I just did is going to give you composition. Let me draw a picture. Okay, so what am I saying here? So if I think about this as being a decoration, so if I have here my F and my G, some element all the ways here, well, what am I saying? I'm saying that if I look at the, this is some F, this is at the star of G, or sorry, this is in X sub star, I guess I have to call it V, don't I? V and W. And here, if this is contained in X of star of W, when I've imposed that by taking that limit, I'm talking about how they're composed together. So given two elements in here, I called it F and now I called it G. F composed in G is now in X of G, plus this contraction. And that's what's going on in the limit. Maybe I should call it X1 of G. And by imposing this, I'm saying, okay, what does composition look like? So I'll just give you a definition now. This is the equivalence of the Sigel condition from category theory in a modular operad. Okay, so the Sigel map Siegel map, how a bunch of graphs are composed, is a map from the evaluation of a pre-sheaf G to its corolla ribbon, which you can think of as just being contained in the product of the evaluation at each of its vertices. And if this is going to be, if you think about what this will be for categories, right? I'm saying that two morphisms are a composite, or if their Siegel map is a bijection. And that's what's going on here. Okay, so the Siegel map is just a map from this graph to this weird big limit, which you can think of as a product. So this is going to be strictly Siegel if the Siegel map is a bijection. Makes sense? And it's a theorem. This is not a particularly hard theorem once you get used to all the words. Is that there's actually an equivalence of categories given by a nerve, between the category of modular operads and strictly Siegel graphical sets. Right, and I have very few minutes left, so I'll just say an infinity or a weakly Siegel. Now I want to weaken this. Well, now I just allow myself to weaken this map. So I take this into simplicial sets or groupoids, whatever my favorite Cartesian category is, and I let it be a weak homotopy equivalence. Okay, and that's a good notion for infinity modular operad. And now in the last 2 minutes, I can take us back to Galois Q. So I'll skip a slide real quick. Well, I'll just tell you quickly. I can build a groupoid out of these pants decompositions of surfaces. And once I take the classifying space, I get down to the classifying space of that mapping class group that I like. Right? So for a homotopy theorist like me, this is a really good way to say the groups are basically the same. But I can work really well with this groupoid that I call SGN. That's what I'm going to say is going on there. And it forms a nice modular operad. So I take its nerve and I can think of it as sitting inside of these graphical sets with the Siegel condition. So I can, just like I was drawing the pictures, those compositions, they come from that Siegel map. And I feel really good about that. And now we get to some actual theorems. In fact, if you restrict, you can get that part of this groupoid, so genus 0 surface is the cyclic part. Well, that's isomorphic. If you take automorphisms or homotopy class of automorphisms, isomorphic to that big group GT. And in fact, the important part is that I can see here, this is as infinity cyclic operads. This is homotopy classes of maps of infinity cyclic or weakly Siegel cyclic operads. But I can see the Galois group here, and it acts the way I want it to. I mean, as close as I can check. So this is homotopy equivalent to the moduli space, and the Galois group acts the way I think it should. So I can now say, what are these elements and where are they coming from? They're really coming from maps. I've like broken it down into its most component pieces. And just in my last minute, I'll tell you that, so we can see how the absolute Galois group here acts. I thought I took that weird pause away. That's the point. So by breaking down that picture that I started with, so I started with the Galois group, I can't write it down. Then I went to this big group GT, I can write down, but it's still huge and weird. Then I noticed the component pieces, and by breaking them into some categorical objects, I can really think about, well, actually it's exactly Tim's question. All of my graphs only get bigger, right? I have very basic components, which are these little stars, these little spiders. If I understand what's happening on these little spiders, I can in fact understand the entirety of this group in like one kind of really beautiful machine just by looking at its actions. And by using the modular part, using these contractions, you actually get a subgroup of GT. It's called lambda by Leila Schneps. And Hatcher. There's one more author. There's another author in there. Schneps and Hatcher define lambda. It's a subgroup of GT, and you can do the same. You can do the same thing with modular operads. You can really break it down, and see that this defines the subgroup. I still got Galois group of Q in there, and I can see all the pieces coming from very small paths. In fact, it all comes from one pair of pants. So if I now understand how the Galois group acts on a pair of pants, I could, in theory, build all of the elements. I cannot, but in theory, that's the that's the point of where we're going. All right, I'll stop there.
Great, thanks, Marcy. So everyone can unmute and clap audibly if you can, or great. Are there questions from the audience? We've already had a few. Let's see.
Yeah, that's all right.
So if you have a question, you can unmute. Looks like Andreas is unmuted. Andreas, do you have a question?
No, I was just unmuted.
Clapping.
Oh yeah. Okay.
Yeah, I know it's right. I just think I think the point is kind of interesting is you start from a really big problem, and by building up the categorical parts, you can decompose it as much as humanly possible, and that actually teaches you something. That's if you didn't understand any of the rest, that's like the point.
That's great. So can you say something about the directionality or orientation of the edges and whether that ended up, I didn't quite see whether that was important or whether it went away later.
It was not important for this problem. So the directionality of the edges, yeah, is it's there because it's well, honestly, because there's not like very good language in the literature about what a modular operad is. There doesn't seem to be any agreement among people about what the definition is. So we use the most general definition. But so the orientation or the sort of duals, the involution on colors. So this C, this doesn't play a role because these are one colored operads, and I just get rid of it. So it doesn't play a role in my example of seamed surfaces. But it does play a role here. So in my example, because at some level, I'm only dealing with oriented surfaces, and I have a really good control over how I can glue. Like I know exactly what I'm doing in mapping class groups. But there are examples where you need this. So so Dan Pedersen has an example, a very similar example topologically, where he uses so using modular operads colored in groupoids. And groupoids for sort of some nice, for studying the moduli space, bundles. And there's also, so compact closed categories would be an example. I'm bad with these words. I always, despite being in Australia, I'm at the wrong, I'm not at the Center for Australian Category Theory. So compact closed categories, or sometimes people will call them traced star autonomous categories. These are examples of modular operads with this involution. But I would say maybe the most interesting thing about having the involution is that all of the other objects that you might think of in operatic worlds, like wheeled operads, cyclic operads, you can see all of them as different slices just by changing this orientation. So this makes it as loose as possible. You can cover all the objects you might want just by imposing direction or removing it, and then restricting your graphs by making them simply connected, etc. So it's kind of a nice thing, but it's so it's the most general thing that could be there, but it doesn't really play a role in my game. It does if you want to play with these compact closed categories and things, if that helps.
Okay, yeah, it does help. Thanks.
Yeah.
Okay, well, are there any other questions?
Can I ask yeah, I was going to ask just like a kind of the like obvious question of, can you like, is there a similar story for higher dimensional field theories, like for, you know, things that aren't surfaces of certain genus, but, you know, higher dimensional manifolds?
Yeah, I have a similar, well, there are examples of like 3 manifolds that are modular operads due to, and I'm gonna not be able to write this name, and I'm hopefully pronounce it correctly. So Geoffroy Jean Siracusa, he's a student of Ulrike Tillmans, did some 3 manifold stuff. If you Google handle body modular opera, it will show up. And then in recent work with, I'm working with some knot theorists. Here we've done some like 4-dimensional knot theory, so surfaces tangled in R4 using the same language, and that is related to this Cauchois-Verne equations in Lie algebra. So there's a lot of quantum algebra. So I know at least a few higher dimensional things. The structure itself is really basic, right? As long as you can give it this combinatorial structure, then you can use the same tools. It's just that, yeah, somehow the gluing of surfaces is so, so certainly when we were constructing the definition of infinity modular opera, like my main goal was that it actually modeled this, because that's what it should be, in my opinion. And then the fact that it actually sticks with other people's ideas of what infinity categories should be is just a coincidence, in my opinion. It's a nice coincidence. It certainly makes it easier to publish, but yeah, it's just a coincidence.
Great. Well, thank you again, Marcy. And
Yeah.
I don't know.
Yeah.
Clap. We see some claps on the chat thingy.
Hopefully,
so
I'm not technically allowed to leave Australia, but I'm supposed to be in MSRI sometime next year, David. So hopefully you'll still be around in Berkeley, and I'll come and say hi.
We'll certainly be around, and I'd love to see you. Yeah, that'd be great.